Our next speaker is Mr. Sean Bond from American Bureau of Shipping, and the title of his presentation is Ship Design for CO2 Transportation. Mr. Bond.
Thank you very much. Thanks very much. Thanks for the organization of this event, and thank you very much for the invitation to come and speak to you about some of the things that we're seeing on the shipping side and the project development side, specifically related to ships and how the carriage of CO2 will likely be carried out. I'm Sean Bond. I'm the Director of Global Gas Solutions based here in the London office. We sit inside of a larger group called Sustainability within ABS, and ABS is a classification society. I believe most or many of you are aware of what classification societies do. However, I would like to just, for those who are outside of that particular group, and we have such a diverse group of people potentially watching this, I thought I would just quickly go over what it is that we do and why we're engaged with CO2 on shipping. So what we are is we're independent arbiters of standards, and our mission is essentially to promote the security of life and property and preserve natural environment. And that with regard to marine structures and offshore structures, typically ships and offshore platforms. We're involved in other areas as well, things like rule development and discussions in forums like this to try to find out how we can assist, at least on the shipping side, and where those seams integrate into the shipping solutions. The way we do this, we achieve this by establishing and administering standards known as rules. And these are applicable to just about every type of marine equipment you can imagine. And we have requirements specifically for gas carriers, and that's where these CO2 carriers would fall. We also have a role within the international organization in the application of international regulations through our status as ROs for particular flag administrations. In that capacity, we apply on their behalf the requirements of the IMO, and we deal with the flag administrations directly with regard to any alternatives or waivers to the requirements that might be necessary in looking at how projects move forward. The statutory activity is distinct from the classification activity. There is a lot of overlap in there. The remits are very similar, but there are things that classification societies put together that are not necessarily in the international regulations. And how we operate is we work with all the various stakeholders in the marine industry to ensure this maritime safety and to apply, ensure that the compliance is met with regard to the requirements and the rules. And you can see here the list of, sort of the dial of various stakeholders, and because of this, interaction between all these parties, this is where we start to get questions when it comes to particular CO2 projects and how things are going to be developed specifically with regard to moving the cargo. We've seen from some of the earlier presentations that there's going to be a lot of CO2. How that's going to get either sequestered or taken to sites for use is going to depend on specific projects, but some of these may have what we call midstream legs that involve shipping, and those ships are going to have to be capable of carrying the cargoes that they're intended within the sets of criteria that are out there for ships and with equivalent levels of safety. I'm going to go quickly over the drivers. You've seen a lot of these this morning, and in fact, you've seen this slide already, so I won't go into it in too much detail. But I think the takeaway point here is that the clients that we talk to and the operators of ships that may be carrying these cargoes are also aware that there's likely to be, in all the scenarios we're looking forward towards decarbonization, most paths have a large amount of CO2 carbon capture, and there's going to be a lot of CO2 to be dealt with, right? So they see that this is a possible area where they'll need to get involved, and the shipping component will have to be fully developed. So the captured carbon, as you guys are all aware, it can either be reused, in which case it would be a CCU situation, or it can be locked in a reservoir, which would just be the sequestration piece. We've heard from both, well, at least one end of these sides of things, but we tend to be in the middle part, which is the transport part. That can take a lot of different forms. The ships themselves have to be able to deal with what's at both ends of the chain, so they have to be designed in order to handle what's being put on at the upstream end, and they have to be designed to suitably offload at the downstream end. And how the ships have to handle the cargo that they actually take on board. And you know, there are things like relative pressures between the ships and the terminals that can have impacts on what the ship designs have to do. And you know, responsibilities for who has to handle which piece of the processing of the cargo is something that needs to be developed. But when looking at these projects, you know, the ship designers have to understand what it is that they're responsible for, what kind of pressures they're going to expect to be taking cargo in at, and how they're going to have to offload it, and what the cargo is likely to be containing. On the reuse side, CO2 is a key input for many industries, feedstock for urea manufacturing, on fertilizer industry, small quantities of food and beverage production, cooling system and water treatment. And there's new demand anticipated as feedstock for producing things like green methane and green methanol as a new generation low carbon fuel. And as far as the capture storage, I know that everyone here is very aware of these kinds of things, but essentially long-term storage is expected by injection into natural porous rock formations such as depleted oil and gas reservoirs, coal beds and saline aquifers, and that allows both sequestration and enhanced oil gas recovery. For a lot of years, CO2 has been injected into hydrocarbon production, such as enhanced oil recovery and enhanced coal bed methane recovery. And the area where we sort of engage with the current group is that the London Protocol Convention sits out there, and this is something that our clients run into when they're looking at projects. You know, and this regards both the movement of waste internationally between countries and the dumping of waste. Of course, the 2009 amendments proposed for allowing transboundary transportation under agreement for CO2 is not yet ratified by the right number of signatories to go into effect. So this is something that comes up with regard to every project. There may be international transshipment of CO2 because depending on how the sequestration sites are located, there may be countries that don't have suitable sites that have to move their CO2 in other ways or to other countries and locations in order to do the sequestration. And there may be other issues as well, including offshore deposition into the seabed, which would then fall under also the sort of the dumping criteria of the London Protocol. And I'll skip this and just focus directly on the carbon value chain. Again, this is the part where we get involved. The transport section right there in the middle, and as I mentioned, the upstream and downstream ends are important for determining how the midstream portion develops. And we sit here in the middle with the transport. So there may be needs for innovative shipping infrastructure, and it has to be established based on however these individual projects form. Right? So getting into the sort of the meat of the discussion with regard to the transportation vessel design itself, just a little bit of background on the CO2 shipping. Current CO2 transportation relies heavily on pipeline networks. On the shipping side, liquefied CO2 is mostly used for food and beverage industry in very small ships at a particular pressure. It depends on what group you talk to, whether this is considered high pressure or medium pressure. I'll get into that in a second. But those vessels operate around 15 bar, minus 25 C. The need for the liquefied CO2 transport is expected to increase based on those sort of demands that you saw in the previous graph, and that may involve scaling up fleet sizes or scaling up vessels. We're seeing mainly moves towards proposed larger ships. There are different challenges depending on how you carry the CO2 that define how big those ships can get and how exactly they're designed. The main challenge for the high operational pressure is that larger capacity tank construction complexity gets difficult, and the thicknesses go up as the pressure goes up and the size goes up, so you wind up with tanks that can be very heavy. So in order to avoid that, we have seen people move towards a little bit lower pressures around the 8 to 10 bar range in order to carry the CO2 at a lower pressure and reduce the amount of steel required for the weight of the tank and the weight of the ship. And then one of the other important issues is composition varies for captured CO2. We've seen already a couple presentations on this morning. And the impurity impact has to be taken into account in designing these vessels. So whatever's going to be in these cargoes has to be accounted for in the design. And looking at just sort of where things stand at the moment, this is maybe not exactly up to date. I think there's a couple new ships, but you can see here, and in fact, some of the Northern Light ships have delivered, as we heard earlier this morning. But there's sort of four, there's 6 vessels in the larger range than the existing fleet. And the existing fleet includes 1 research vessel and several of the small beverage quality CO2 carriers in those higher pressure ranges. How we deal with these depends largely on the CO2 characteristics. The CO2 properties that we're mostly dealing with is the fact that it's non-flammable, it's an asphyxiant, it's heavier than air, and it has a phase diagram as indicated here on the right, with a triple point at around minus 56 C and 5.18 bar absolute for pure CO2. There are things about impurities that can change that a little bit, and those have to be accounted for in how you set up, for example, the safety systems on board to do shutdowns when you start to get near the triple point. As someone mentioned, it's likely that the CO2 will be carried as liquid, and so there are certain limitations because at atmospheric there is no liquid phase, so you have things happening on the sublimation line if you go below the triple point. So this has to be avoided when the cargo is being carried as a liquid, right? So what pressure you wind up carrying that liquid at saturation will define the temperature, and it may have impacts on how you decide to do the cargo cooling or the cargo handling. There are toxicity concerns at higher concentrations. Again, here's a list of some of the references. So 5,000 ppm under OSHA, 30,000 for ACIGIH, and 40,000 is immediately dangerous to life or health. And these are things that need to be considered. As currently outlined in the IGC code, which is the IMO requirements that would apply to the ships that would carry the liquefied CO2, it's currently defined as an asphyxiant. There's movement afoot to change that to toxic, but there's no, and then you can see in this table certain other features of the ship that have to be followed in order to comply with the requirements. A Type 3G ship is a ship that typically has the least strict requirements when it comes to certain requirements. The toxicity aspect won't change that particular element, but there will be additional requirements that would get pulled in by the definition of the cargo if that goes through. So some of the risks in carriage, there's the risk of the cargo solidifying, freezing rather than sublimation, but in order to deal with this, the way that the codes have been written is to have low pressure alarms at 0.05 megapascals above the triple point. This should help. And at that level, you would wind up shutting down all your systems if you had a sudden pressure drop that could potentially wind up with some solidification or freezing of the vapor or the liquid phase. And on low pressure, you'd automatically close all the valves, shut everything down, stop the cargo compressors, stop the pumps, and put the ship in a static state in order to make sure that things can be maintained at that level. Means of isolating the cargo tank safety valves need to be provided. One of the issues is if you're carrying the cargo, which you will be at a pressure above the triple point, if you have vapor releases, the cargo cooling associated with the gas expansion can result in things like ice formation, and if that happens in a relief valve, you can wind up with a valve that's stuck open. So there's a particular requirement specific to CO2 that calls for the relief valves to be able to be isolated so that they can be cleared if they were to happen to pop and then stick open. Right. Other aspects related to that, there are certain things where on gas carriers you typically would see screens in the vents, but those wouldn't be permitted on a CO2. They'd be required, in fact, in the case of many cargoes, but on the CO2 carrier they would be required not to be included for this for the very reason of this, this freezing issue. In the case of reclaimed quality CO2, the materials of construction need to be considered so that they can handle whatever the impurities are. Now, there's a huge list of impurities. I have a list that's smaller than our colleagues from Australia showed earlier this morning, but I will put it up, and I would second Linda's request for data to keep coming in on this. One of the things that we see from the project developers, or at least a certain segment of the project developers, is a need to shrink that list and identify what kind of limitations ought to be placed on the cargo so that the ships can operate suitably. Again, it depends on how the projects are developed and how closely the shippers are working with the terminals as to who has the responsibility to, remove or handle, particular elements of the cargo. So again, the density of CO2 is heavier than air. So if you do have releases, they will drop. Right? Depending on the ship type, you'd need to then have suitable ventilation and suitable detection to understand that you've got a leak and to be able to control it. It can also be, as I mentioned before, it's an asphyxiant hazard, and there are toxicity levels associated with the carbon dioxide that would need to be considered. And this is not something entirely new, because we do see it with regard to firefighting systems, for example, which use CO2, but it's an issue that we need to address in the design. And if you look at the sort of typical operating range, you can see these are sort of the two pressure areas that we see the most interest in at the moment. There are other considerations at different pressures than these, even higher, but these are the areas where you would see the typical two ranges, shall we say. One would be for the what we call high pressure tanks at around 18 bar, and the other the lower pressure tanks just near the triple point at probably 8 to 10 bar. The IGC code does refer to reclaimed quality CO2, but it doesn't give any very specific information about it. It just indicates that it has to be addressed by, the designer, and the ROs would be, checking what's being done. So typically, you would need to see additional work around those impurities done on a ship-by-ship basis. Annex B of ISO 27921 provides some indicative impurity levels. We've seen some industry standards as well. We've seen several lists this morning in some of the other presentations. But the cargo purity composition depends on various parameters: the carbon capture technology and process, the CO2 onshore handling and storage facilities, and the impurities effects can be things like thermophysical effects, corrosivity that makes you have to, maybe potentially rethink some of the materials, how the reliquefaction plant is able to handle some of the non-condensables, and the health and safety considerations of certain of the impacts, or the impurities. And corrosion depends on water content and solubility. CO2 dissolves in water and forms carbonic acid, and those effects can also come from some of the other impurities. And this is a list of just some typical ones. Again, in addition to individual impurities and the impact on some of the physical properties of the cargo, there may be interactions among them, and this is one of the reasons that the bigger the list gets, the more the difficulty increases, because knowing the interactions between all the potential impurities can get fairly daunting. So we try to focus on the most critical ones and the ones that are most likely to be in the stream. The cargo tanks themselves, there's a lot of different, there's 3 main tank types used typically and included in the IGC code. Only really Type C tanks are suitable for carrying CO2 because of the pressures involved. So the Type C tanks are pressure tanks, and then at those pressures, and with the liquefied gases, there's compliance with cryogenic requirements that are required, and the pressure that's selected as the operating pressure and the maximum pressures are the ones that drive what those temperatures are. And in particular, the lower pressure end. That also drives the temperature selection for the design. Impurities in CO2 can potentially pose material issues, as I already mentioned. There are considerations for development of new materials in progress for larger tanks. The typical tank types that we see are cylindrical bilobe type C tanks. The cylindrical tanks tend to be the higher pressure tanks, and the bilobes tend to be at the lower end of the pressure range. But the geometries of those tanks tend to allow for more cargo for the same size ship. And thick, low-temperature steel plates require special consideration when welding. So if you're looking at, for example, a steel tank with a very large, multi-lobe configuration, the welding needs to be specifically considered to be suitable for the plate thickness and the temperatures. Designing around the triple point, I think I've covered that already fairly well in the blockage of the pressure relief valves. Continuous monitoring of the pressure and emergency shutdown associated with low pressures is something that we have to do on the ships. Permanent fixed gas detection for cargo tank hold spaces. The cargo control room and other enclosed spaces where CO2 can be accumulated needs to be provided, and a restricted level gauging system is permitted. So looking at boil-off gas management while sailing, again, we're sitting in this triple point area, right? So there's a couple different ways that boil-off gas can be handled. It can either be handled by pressure accumulation or by reliquefaction or subcooling, some other kind of cooling. So if you go with the pressure accumulation route, then you do have to have a holding time calculation that shows you can maintain the cargo for the period of time that it would be necessary in order to get the cargo offloaded. Operational environment and cargo and loading temperatures will have an impact on that assessment, and including the operating profile, loading level, its cruising range, local restrictions in some areas. And tank pressure control during discharging is going to be important, as I mentioned already. The compatibility with the loading facilities and the offloading facilities need to be considered, and how those projects actually look also may have impacts on the ship design. So if you have what you could either be having a ship delivering to a shore-based terminal and then sending it off to a treatment center before injection into the ground, or some other kind of storage facility. There may be offshore, floating terminals taking CO2, in which case the interaction between those terminals and the ship has to be considered. There's several configurations that we've seen being discussed, and in each case, these discussions tend to be fairly bespoke at this stage. So just getting into the conclusions, carbon capture is generating interest in CO2 carriage by ship. This will develop depending on the actual carbon projects, and we're seeing quite a few. Designs require require project specifics from the upstream and downstream end to define the vessel specifications. The regulatory framework, including the London Protocol, need to be well understood by the stakeholders. The technical requirements and standards for ships are mature. I mean, we already have vessels carrying CO2. There may be some new technologies that come into this, and there may be risk assessments around the project overall that have to happen. Understanding how the additional requirements of localities, ports, coastal states may have impacts on how those requirements apply and what applies. But by and large, most of the technologies are mature. Impurities drive the cargo definition and are highly relevant to the ship design. So again, collecting that information and understanding what the carbon capture streams are producing and how much treatment will be done on shore and what's going to go on board the vessel will be important to getting these projects to happen suitably. And early cooperation among stakeholders in the full chain is the optimal path, because then you can understand up front how what you have to deal with, and we've been seeing a lot of that. So I will leave it there, and thank you for your attention and your time, and open for questions.
Thank you, Sean, for your interesting presentation explaining the role of shipping in the CCS value chain. I will now open the floor for questions. Greenpeace, you have the floor.
Thank you, Chair, and thank you for that very interesting presentation. I think it gives us an insight into an aspect of this that we've not really talked about so far within these bodies, so it's extremely useful. I had 3 questions. Firstly, in relation to contaminants that may be associated with the CO2 that would be loaded on board, and to understand whether there's a possibility of separation and condensation of any of those contaminants during the transport, and what the implications of that would be for then loading up with the next cargo. You know, could there be interactions that could limit the number of different sources of CO2 that could be loaded into one vessel over time? Secondly, are there any circumstances where you would need to be looking at venting one or more of the tanks on board a vessel while it's at sea? I mean, are there any safety conditions where that would become a necessity? And thirdly, in the unlikely event, perhaps, of a casualty, a shipping casualty, where the vessel is damaged, is there anything that can be done in order to recover the cargo from one of these things? Or would it inevitably be in a situation where you would just be managing the release of that CO2 on the vessel? Thank you.
Yeah, thanks very much. All very excellent questions. When it comes to contaminants, yeah, there could be interactions between CO2s from, if you were going to be a very flexible ship and move from terminal to terminal with different specifications, that would be something that would have to be considered in the design. Well, would be best considered in the design phase. So understanding how flexible the ship needs to be would be important. But again, cargo definition would be the key, right? So the ship designer is kind of the end user of the information about what the cargo contains, and so they would need to collect that from either the various sources and do that kind of an assessment, and or otherwise somehow specify to terminals potentially what they have to do on shore. There are other permutations of this. We saw a slide someone else put up about a sort of a hub and spoke collection situation where you have multiple emitters, possibly with different emission streams, and how that would be controlled at the hub where it all comes together. If it's going to be moved at that point by a shipping solution, that would be where the cargo definition part would have to happen, right? Now, there may be things that you can do in ship design depending on, I think there's going to be a cost associated with how much cleaning you do on CO2 when it's on shore. There's going to be a cost associated with the ship depending on how much of their own control they have to have on it. For example, if they have to change their cargo handling equipment in order to handle the impurities that aren't being removed, then that would shift to the ship. And then what happens at the other end is important as well, but that isn't so much related to the impurity content of the cargo. Though there can be issues at the downstream terminal if they aren't prepared to take the CO2 impurities that the ship has. We've sat in some projects where all the players were together, and those are the ones that tend to work the best, especially if they're developing together, because then they can jointly have those discussions and say, we need to design our terminal to be able to handle this, and so the ship can, there are these kind of multi-party, multi-stakeholder discussions to be held, right? So the more jointly the project develops, the better, the more accurate the final outcomes would be. When it comes to venting at sea, there are a lot of safeguards within the written codes to avoid releases. That's the intent. The reason that you might have emissions that fell outside of that would be some kind of other event that resulted in, for example, pressure rise in the tank and a lifting of the relief valves. There are hazard scenarios that in which that can happen, but the intention is not to release, right? Not to release at all, and then in addition to have the additional safeguards on the relief valves, so that if one were to open, it would either close or would be able to be isolated and with another active relief valve available while that valve is cleared. There are, in an extreme case, ultimately the safety of the crew and is what would take precedence. So if there were an event in which it was a matter of life on the vessel, then that would be where a release could happen within the understood parameters of how the codes cover the design. Right? The casualty case, I can't really answer that, unfortunately, but I don't see a way of recovering the CO2 easily, right? There may be controls in accident situations that could be available and put in place, but once it's released, it would be fairly difficult to recover unless it's on board, right?
Thank you, Greenpeace, and thank you, Sean. Australia, you have the floor.
Thanks, Sean, for the interesting presentation. I know it's very early on, but are you starting to see alignment on CO2 specification within vessel design?
Right now, I think the industry was waiting for someone to take the first step, right? So we're seeing a lot of projects now that there are projects that are defining their own cargo specifications, but we're seeing a lot of people default to some of those existing, competitors, or I don't know if competitors is the right word, but the existing industry developed specifications, at least as starting points, right? As you said, it's fairly early, so that may be a starting point for design, but once things drill down and the projects are better defined and the actual emissions are identified, you'll probably see changes, tweaks to that, unless members of the project commit themselves to treating the stream so that it contains whatever's in that spec. Right? So, we're seeing people like as a first point looking at what others have done. Right?
Thank you, Australia, and thank you, Sean. Seeing no further questions, we will now break for lunch, and we will reconvene at 2 p.m.
Thank you.